The next concept we are going to discuss here is clocking of flip-flops. So the timing for any sequential circuit, for which we do have several timing considerations whenever we are designing any finite state machines or any sequential circuits, for which we need to undergo the following objectives, like to define the following global timing parameters and show how they can be derived from the basic timing parameters of flip-flops and gates. Like we need to discuss about maximum clock frequency, maximum allowable clock skew, global setup and global hold timings also. And apart from this, we are going to discuss about the ways to control the loading of data, how the data is loaded into the registers. All these concepts comes under clocking of flip-flops. So we discuss in detail about each and every terminology step by step. First thing is maximum clocking frequency. So what is this maximum clocking frequency? The clock frequency for any synchronous sequential circuit is generally limited by the timing parameters of the flip-flop or the logical elements like logical gates in the circuit, because even though the clock is supplying to the flip-flops, this frequency, that means the clock frequency for this synchronous sequential circuit is limited by, who is limiting the clock frequency? Because of the presence of D flip-flops, or it may be because of the presence of some logical elements. The clock frequency should be limited. Okay, now the minimum clock period is reciprocal of this clock frequency. What is the time period we are going to maintain for a clock? That will be a reciprocal for your clock frequency. Now I would like to give an example here. I am having a 40 feet road, and at the same time I am having an ORR, outer ring road. So I have been provided with a city 100. So the maximum permittable speed on ORR for a bike is, let me take with an 80 kilometers per hour. Okay, the same 80 kilometers per hour, this amount of speed I cannot use on my 40 feet road, right? And the same, in the similar manner, the 40 feet road is provided with a speed limit of, let me say, with 30 to 40 kilometers per hour. The same thing I cannot use on the ORR, because on the ORR many number of vehicles with a greater speed they will be traveling on the ORR. So that means on the road, whatever we are going to take, we need to aware of the road properties or the traffic rules we should aware of. In the similar manner, the maximum clock frequency, like a clock frequency, I cannot give you a random value for any sequential synchronous circuit. So this clock frequency or this clock speed is completely dependent on the logical elements or the blocks that your synchronous sequential circuit is accommodating. Okay, so the clock frequency I cannot give randomly. Like the maximum clock frequency F max, I will say, let it be the highest frequency F max, at which a flip-flop can be reliably, because these are the two flip-flops I am having in the circuit, and they can be reliably triggered. Okay, so for example 10 megahertz is the maximum clock frequency. If I cross this maximum clock frequency limit, like I have given here as 12 megahertz, these two flip-flops cannot be triggered. That means they cannot give us the faithful results. Okay, so if the clock frequency is above this maximum clock frequency, that is F max, the flip-flop would be unable to respond quickly, these two flip-flops, and its operation is not at all reliable, will not be reliable. So this F max limit will be varying from one synchronous circuit to other synchronous circuit, or from one flip-flop to other flip-flop based on the elements the hardware circuit design is going to accommodate. Based on them, your maximum clock frequency will be decided. So now what happens generally, basically the output for a flip-flop will not change the state immediately after the application of your clock signal or asynchronous input, because let me give an example. The output, initially my output of a signal is logic 0 for my flip-flop, day flip-flop. So as soon as I am applying the clock signal, I may not have the transition immediately. That means certainly and definitely some amount of time will be consumed. That is the time interval between the time of application of your clock signal, that means triggered edge, and the time at which the output actually makes a transition is called the propagation delay of your flip-flop here. Okay, that is indicated by TTFF. Okay, that means the propagation delay for my flip-flop, it may be from, like, the output may have a transition from logic 0 to logic 1, or it may have a transition from logic 1 to logic 0. So if it is having a transition from logic 0 to logic 1, means the initial state of my output is 0, and if it is having a transition from logic 1 to logic 0, means the initial state of my output is logic 1. In this manner I can able to explain you the propagation delay. So my final agenda is the maximum frequency, the F max or the maximum clock frequency I need to find out. It all depends upon the associated elements in the design. Okay, so the associated elements may be the logical gates, or it may be the flip-flops. So definitely gates and flip-flops are going to decide my maximum clock frequency, right? Now for the gates, definitely it's going to have some propagation delay. For the flip-flop also there will be propagation delay. Apart from it, we do have the setup time as well as the hold time. So in the propagation delay also, we may have minimum value as well as maximum value. That is TPLH, gate output transition, to have logic 1 from logic 0. That means logic 0 to logic 1, if there is a transition at my gate output, we call it as a TPLH, and it may have a minimum value and it also may have a maximum value. Similarly, if my gate output transition is having a transition from logic 1 to logic 0, that is TPHL, I going to call it as. So it also going to have minimum value as well as the maximum value. Similarly for the flip-flops also. So whenever we are going to consider the flip-flop, we need to keep an eye on the setup time as well as the hold time, because we have seen what is the contribution of setup time and hold time during the discussion of timing checks, right? So now this setup time as well as the hold time also plays in deciding the factor of your maximum clock frequency for any, see, like, that is going to be applied for any sequential circuit. Now let me take an example here. I am having D flip-flop. So the input for the D flip-flop is one is a clock signal, that may be an asynchronous input, and one more signal is D, and this is my data signal, and the input for D is taken from your Q bar, that is one of your output signal here. Okay, so clock signal you can see here, clock, and this will be the time period, because clock is nothing but it is a kind of a pulse. So this is my on time and this will be my off time, and this is entirely my time period, that is TW. So as soon as I am applying the clock signal, am I having any output transition immediately? Never, because certain amount of time definitely the flip-flop consumes, and this amount of time is nothing but the propagation delay of the flip-flop. Okay. Now you can see here that, so one second. Okay, so I am having here in this manner. You can clearly observe that Q is having a transition to logic 1 uh, not as soon as a clock event is happening, because this is my clock event, that is rising edge of a clock. As soon as the rising edge of a clock is given to the D flip-flop, immediately I am not having here a transition at my output side. So certain amount of time it is taking. That means I am going to call it is the propagation delay for my flip-flop. That means as my initial state of my output of my flip-flop is logic 0, and it is taking to logic 1 after certain amount of time, after the application of your rising edge of a clock or this clock event. So the amount of time at which the time interval between the time of application of the triggered edge and the time at which the output actually makes a transition is called your propagation delay of the flip-flop. Okay. Now, so next positive rising edge of a clock is happening at this time, right? Here, this thing. So this is my next clock event. I'm mainly focusing on rising edge of a clock only here. So this is one clock event and this is one clock event. So before the clock event, if my output is stable, if my output is stable, I am going to call the duration, this duration is nothing but setup time. And if the signal, because Q is also nothing but Q is what here, it is some kind of a data. Q is only a data, so can I call this one now as a data, some kind of a data signal. Now before the rising edge of a clock, my data signal, if it is stable, I am going to call it as a setup time. Okay, and after the rising edge of a clock, for some particular amount of time, I am going to call it as a hold time. So whenever your data is stable before the rising edge of a clock or after the rising edge of a clock, if it is stable means the flip-flop is not under the violation. This is what I can able to say. Okay, so let me find out the time period, because the minimum clock period is nothing but the maximum clock frequency for your circuit. Okay, so let me find out the time period here. TW should be greater than or equal to TW, this is time period, is greater than or equal to maximum of propagation delay of a flip-flop plus setup time of your flip-flop. So setup time of your flip-flop. In this way, the time period is represented in terms of propagation delay of a flip-flop plus setup time of your flip-flop. Okay. So as it is given here with some values, TPLH minimum and TPLH max and TPHL max. Okay, so here they have given here as 40 nanoseconds, one is 25 nanoseconds, and setup time for your flip-flop is 20 nanoseconds. I need to find out, because here max of TPFF only I have to take into account. I no need to consider about minimum. Okay, so max of TPLH plus TSU one is, or max of TPHL plus TSU, because I don't know what is my initial state of the output of my flip-flop. That is why it may be from logic 0 to 1 transition happens, or it might have a logic 1 to 0 transition might have also happen. That is why. So in this manner I can able to find out the TW for this circuit, the time period for my clock is TW should be greater than max of t is 2. So 60 nanoseconds will be my answer. So let me have one more small example. So in the previous example, you can see that Q bar is directly connected to data input. Now in the present example, Q is connected to data input through an inverter. Now how will be the timing diagram? We are going to see. So initially my Q is at 0 and will change the state after the propagation delay of the flip-flop to logic 1. And parallelly and initially D will be at logic 1 and it will change the state after the inverter delay addition to Q. Okay. Now, so this is my clock signal as usually. So Q will be changing its state from logic 0 to logic 1 after the propagation delay of the flip-flop. So here clock event has happened. Immediately clock event for Q won't happen here. It certainly takes certain amount of time, and here the event has happened. So this is the propagation delay of the flip-flop. Now this Q is passed through an inverter and to the data input. So as soon as Q is not directly connected to data input. So Q is connected through an inverter. That means if it is logic 1 here, if it is a data event is happened here, means immediately for the D signal data event will not happen. Okay, because I am having here in between inverter. So inverter is also giving us some delay. It is also contributing some amount of delay such that D will be having an event happened after the addition of the propagation delay offered by the inverter. That means I said that initially Q is at 0, initially D is at 1. So Q will be having logic 0 to logic 1 after the propagation delay of the flip-flop. D will be having a logic 1 to logic 0 after the propagation delay of the flip-flop plus after the propagation delay offered by the inverter. So these two elements, after that it is having a logic 1 to logic 0 transition. Okay. Now I need to find out the TW in this case, that is time period. TW, I expecting that TW equal to greater than equal to TPFF plus TINB plus setup time of the flip-flop, because again rising edge of a clock is happening here. So this is my setup time of the flip-flop for which this data signal is stable. Okay. So let me check the equation. Yes, it is right. TW is greater than maximum TPFF plus maximum of TP propagation delay of an inverter plus setup time. So I do have one more example here. So this is my clock signal, synchronous circuit it is, and here first D flip-flop, second D flip-flop. So D Q0 is the output and Q1 is the second flip-flop output, the clock Q0. So because of propagation delay offered by the flip-flop, it is having a event here and D1. So this Q0 now it is not feeded back to here like this. It is passed to something else. That means it is passing to the second flip-flop input. In between I am having a multiplexer. So definitely multiplexer is also contributing as a delay element. Now D1, this D1 is nothing but propagation delay of this flip-flop plus propagation delay of multiplexer plus setup time for this one, for the second flip-flop. Okay, these all the things comes into picture, because anyhow these two clock signals are synchronous with each other. So definitely if it is a positive edge of a clock, means here also I will be having a positive edge of a clock. So these two clock signals anyhow they are same. So here a clock event is happening, here also a clock event is happening, because I am focusing on positive edge of a clock only. Now the time period is nothing but it is a summation of propagation delay of the first flip-flop plus propagation delay of the multiplexer plus setup time because it is the event before the rising edge of a clock. Your incoming signal or a data signal should be stable. So this is my setup time. So the same thing here, it is reflected also here. So we can able to see here setup time is this one. This is the one. I'm talking keeping in the mind with respect to D1. With respect to D1 signal, I am finding out TW, that is time period of the clock, such that I can find out what will be the maximum clock frequency. So TW is greater than TPFX plus TPMX plus TSU. In this manner it happens. So I do have one more small example. The logical elements present in the circuit are one OR gate, one AND gate, two flip-flops are, one is D flip-flop and one is JK flip-flop, for which the propagation delays are mentioned along with the setup times, and for the logical elements we do have only propagation delays. So how many paths are there? Because without path I cannot able to find the time period TW. Any path from Q1 to Q1? No. Any part from Q1 to Q2? Yes. Q1 like this here, and passing to JK flip-flop, and next Q2. One more. From Q1 to Q2. From this one, Q bar of the first flip-flop, next to AND gate, next to JK flip-flop of this one, next to Q2. Is this right? Yeah, it is right. So whenever I am finding out Q1 to Q2, that means first part, Q1 passing to JK flip-flop and Q2. That means this Q1 is happened. The Q1 signal, that means the Q1 will exhibit the output after the Q1 will be exhibiting something that has happened due to this flip-flop, right? That means some signal have propagated through this flip-flop and Q1 has its state change. That means some propagation delay of this flip-flop comes into picture now. Q1 came into active mode means definitely this flip-flop contribution is definitely going to present. So this flip-flop contribution is present means some signal has triggered this flip-flop, right? So that means propagation delay of this flip-flop plus setup time of the upcoming flip-flop is nothing but part from Q1 to Q2. This much amount of time this part is consuming. Okay, that is 20 plus 10 nanoseconds. Next part is Q bar to AND gate, through AND gate and through JK flip-flop. So Q bar came into one level means definitely there is a contribution of the first flip-flop, which is nothing but propagation delay of this flip-flop plus AND gate propagation delay plus upcoming flip-flop setup time. So how much I got here? 42 nanoseconds. In the similar manner, Q2 to Q1, are there any parts? Yes, Q2 is this one. So Q2 through AND gate and again to Q2. Q2 to Q1, right? Q2, OR gate, Q1, this flip-flop and Q1. And Q2, yeah, that's it. There are no more parts, only one part is there. So that means Q2 got a transition means it is because of this flip-flop propagation delay plus OR gate plus setup time of the upcoming flip-flop, that is TDSU. Okay, 25 plus 10 plus 5, that is 49 seconds. And from Q2 to Q2, anything? Yes, Q2 AND gate, again this one JK flip-flop. So Q2 had a transition means definitely it is because of the previous flip-flops propagation delay plus AND gate plus upcoming flip-flops setup time. So in this case the previous flip-flop and upcoming flip-flop are the same. That is setup time for JK flip-flop, that is 25 plus 12 plus 10 equal to 47 nanoseconds. So among all these parts, according to the concept of lumped delay, that we need to consider. So 47 nanoseconds is the longest part, or it is the maximum delay offered by the circuit. Hence, once I got this maximum path delay, that is nothing but TW, I can able to find out the maximum clock frequency, because once I have got the value for TW, I can able to find what is the maximum clock frequency that I can apply to my entire circuit, such that the elements like JK flip-flop or the D flip-flop, logical AND gate or AND gate and OR gate will give me the faithful and reliable results. So these are the concepts of clocking of flip-flops, and the next thing is clock skew. So what is a skew here? If a clock edge doesn't arrive at the different flip-flops at the same time, for suppose, like I'm having here a many number of flip-flops, like in the previous case, I'm having here a synchronous circuit. Okay, so CK is connected to D flip-flop as well as CK is connected to JK flip-flop. In between, for this flip-flop, if the and for this flip-flop, if these two flip-flops are not receiving the clock at same amount of time, like it is receiving the clock prior than this flip-flop, that means this flip-flop is skewed. That means in this part some element is there that is offering certain amount of delay, because of which this flip-flop is getting skewed. That is the concept of clock skew. Okay, so that means the difference between the time of arrival of the clock at the flip-flops is nothing but the amount of clock skew. So I have already said you, it is maybe happens due to different delays in different parts, like from clock signal, from the main clock generator signal to different flip-flops. It may occur due to buffer delays or inverter delays or wire delays or any combinational circuit delays also. So let us involve with the concept with an example. So clock C2 is not skewed after C1. This is one flip-flop, this is first flip-flop, it is a second flip-flop. So here C2 is not skewed. That means inverter here it is offering 0 amount of delay. And let me demonstrate the waveforms. C1 is a positive edge of a clock and C2 is completely a negative edge of a clock. Right. So now Q1, this is happened because of the previous flip-flop's propagation delay. So I am having a transition here. Next logic 0 to logic 1. Okay. This Q1 is passed as an input to your second flip-flop, that is D2. So in between I do have here an OR gate. So definitely OR gate is having its own contribution in providing the delay. D2, propagation delay of the flip-flop plus OR gate contribution. After that the D2 is having a transition, because Q1 is having a data transition from logic 0 to logic 1. That means this transition have to be sent to D2, right? That means this information have to send to D2. From 0 to 1 I have taken here, so you are also going to take you are also going to receive 0 to 1, because I am sending you 0 to 1, so you are going to receive the 0 to 1. So this 0 to 1 won't happen immediately, because I am having here in between OR gate. This OR gate is contributing some amount of delay, because of which 0 to 1 is getting delayed because of the presence of OR gate, and it is offering some amount of delay, right? And after that 0 to 1, next it is in one state, logic 1 state. So as the clock is not skewed here, that means inverter is not offering any delay. So I can able to find what is TW. It is nothing but propagation delay of the first flip-flop plus propagation delay of the OR gate plus the setup time of the upcoming flip-flop. Okay. So this will be the equation as the clock is not skewed. That means inverter or some logical element, not exactly an inverter. You can take any kind of buffering element also is acceptable. Now, if the clock C2 is skewed after C1, what happens? So, This is initially my circuit. C2 is skewed. That means because of the presence of inverter, by certain amount of time, my C2 got shifted right side. Okay, because flip flop one is a positive, passage. It is a passage flip flop and it is a negative edge flip flop. Okay, so this negate got shifted a bit right side, and here also the neck edge got shifted a bit right side because of the presence of TINV. How much amount of time it is getting shifted right side means it is because of TINV, that is like a skew offered by the I inverter TINV. Now, so this Q1 is completely dependent on this clock C1, right? So because of the propagation delay of the first flip flop, Q1 has a transition from 0 to 1 like this. And now coming to your, what do you say it is, your D flip flop and D2. So D2 is propagation delay of the first flip flop plus OR gate I have here. Next it is having a transition from logic 0 to logic 1. It will be remaining in logic 1 only. So that means here I need to consider TW keeping in reference of the second clock. That means this flip flop clock. So that means here anyhow the delay is, if the C2 is shifted towards right side, the C2 is shifted towards right side means TINV is already added here. Okay, so by which in the TW, if I am going to find my TW, okay, so that means it is nothing but propagation delay of the flip flop plus OR gate plus a TSU. It is already added, TINV is already added here. Now I need to subtract TINV. So minus minimum of TINV. Okay, or in this waveform also the same thing, the same explanation can be done, because propagation delay of the flip flop, this one D2 with corresponding to C2 signal, it is because propagation delay of the flip flop plus a TOR gate plus this is my setup time. Okay, this is the original one actually. Okay, and this is because of the addition of TINV. That TINV you can able to find out here. So in order to find what is the actual value of TW, I need to definitely subtract it minus TINV. So that is the concept if C2 is skewed after C1. Next, if C1 is not skewed after C2, so that means the same thing, the same explanation. C1 is not skewed means both first flip flop and second flip flop are receiving the clock at same amount of time, and I am going to have the equation like this in this manner. Now C1 is skewed after C2. So C1 is, that means clock CK is directly connected to C2. After that C1 is getting the clock signal. That means can I shift my C2 signal towards the left side? Because or otherwise C1 signal can be shifted towards the right side. Any of it is possible way. So let me shift my C2 priorly, or otherwise C1 is right side of C2, because now it is my reference signal C2. So now applying the same thing C1. So D1 is happened because of the propagation delay of the flip flop, and D2 is happened because of TPFF plus TOR gate plus TOR gate, and it will be from logic 0 to logic 1. Now as the C2 signal is advanced here, because clock C1 is skewed after C2 means C1 is getting shifted right side, or C2 is getting shifted left side. Okay, now C1 is a delayed signal, otherwise C2 is the advanced signal I said. Okay, because in receiving the clock. Now TW can be find out by, it is advanced signal means like before starting only it is advanced. That means you like in order to find out the time period, that is with respect to C2 signal, with respect to C2 signal, that means TINV by TINV times it is advanced. C2 got advanced. That means before only it had started. So see, if for suppose C1 is started at 0 seconds, that means C2 might have started at minus 2 seconds. So it had started at minus 2 seconds means what is my agenda? I need to find out TW. So these minus 2 seconds have to be added here so that I can able to get my TW. So TW is nothing but with respect to this C2 signal, D2 signal, TW I need to find out. So this is nothing but TPEFF plus TOR plus setup time plus this. What is this one? This area. This area is given by this one. Otherwise this one. Yeah, you can able to see here also. So yeah, this TINB. Okay. This area or this area both are same because TINB is the only matter that is having showing an impact on C1 and C2. So that means with reference to C2 signal, D2 data signal is represented, that is TW equal to max of TPFF plus max of TR plus TSU plus maximum of TINV. That means whatever it is started earlier, that have to be compensated by addition of TINV signal. In this way C1 gets skewed after C2. So in brief, in summary, so if C2 skewed after C1, you will be getting minus minimum TINV. If C2 skewed before C1, that is C1 skewed after C2 means max TINV have to be added here. Now, coming to the concept of global setup and global hold. So what is the contribution of them? We will see now. So yeah, this is the right slide. I was searching for it only. Right. So I am having here D flip-flop, data is connected, and CL key is the clock source or the clock generator or the clock signal. It is passed to a buffer. So definitely it is offering some delay. So this is a global clock signal and this is my local clock signal. So clock signal, local clock signal. So because of its impact, it is getting shifted right side. So how much amount of time? That is decided by this propagation delay offered by this buffer. Okay, that is by TC amount of time. So initially this is my data flip-flop, that is D flip-flop. Is having some data. This is going to receive, T input is going to receive some data signal, and so before the rising edge of a clock and after the rising edge of a clock, your data signal should be stable such that there should not be any violation. Okay, this part is stable. This green line is nothing but global clock signal. This blue line is nothing but local clock signal. So global clock signal is global green in color. That means I am indicating with TSU, its setup time, and correspondingly its whole time will be TH, capital TH and capital TSU. Due to the involvement of buffer, my local clock signal is having in this scenario such that because of the presence of local clock signal, because in the previous class I hadn't considered the buffer. That means global clock signal is directly attacking the D flip-flop. Because of the consideration of the buffer, local clock signal is attacking the D flip-flop, and what happens to its setup and hold time will check. So because of which the setup time is getting extended, you can able to see here, that is given by TSU, and because of which your hold time is getting reduced, you can able to see here when compared to the previous case. So small TSU is given by capital TSU plus minimum of TC, that is delay offered by this one, and capital TH is nothing but small th is nothing but capital TH minus max of TC. So that means finally what I would like to say is, because of the addition of buffer here, I have generated with local clock signal that has shown the impact of on setup and hold time, such that the setup time had increased and the hold time got decreased. These are the effects of global setup and global hold times. So in this case also, I am having here if for suppose data is also getting delayed, so X is my data signal, it is passed through some logical element, I am going to get a D signal, that is data signal. So X is my logical element here. So green corresponds to global clock signal, X corresponds to original data signal, D corresponds to delayed data signal. Now the data signal is getting delayed by how much amount of time, that is T net, you can see here. Okay, this is the X table is nothing but D table but with a shifted amount of time, that is T net. Okay, now that because of the presence of buffer here, CK local clock signal is this one, which is indicated by the reference event of the local clock signal is indicated by blue color, and the reference event of global clock signal is given by green in color. So finally you can able to find out the global setup time as well as the global hold time in terms of your local setup and local hold, as well as the delay contributed by this element as well as this element. So I will give you one example, and it is all your wish to find out the rest of the thing. So TSU, that means because of the local clock signal, setup time, local setup time had increased, that is TSU equal to T capital TSU plus minimum TC. Okay, so at the same time, can I say my net which is got shifted right side has to be decreased according to your global clock signal? So that means my capital TSU is nothing but, that means this one green color, capital TSU is nothing but this T net, because of T net is shifted here, plus TSU of your TSU minus minimum of TC, that means maximum of T net, that means this element, and this area is given by TSU, that is this one TSU and minus TC, this element have to be like removed, because I need only this one, right? This one means that this have to be removed, so such that I can able to find out. That means TSU can be expressed as T net plus TSU. TSU is from here to here, this is TSU. So I need from here to here, such that so if I want to obtain from here to here means this portion have to be removed, that means minus minimum of TC. In this way T capital global setup time can be realized. Similarly, it is global hold time can be obtained like this. So this is the global hold time I need to find out. It is nothing but capital TH, that means from here to here, small t, capital TH is expressed as small th plus maximum of TC, only, right? This is TC, because I am concentrating this TH is nothing but TC plus TH, but this portion I don't require, right? This portion is given by this one, so minus T net. this logical element have to be removed. In this way, global setup and global hold can be found whenever the data is delayed or whenever the clock is getting delayed. So here it is a small example, very easy example, clock. So finally y is impacted because of the clock signal. As soon as the transition at clock signal is happening, there immediately I don't have any transition at my output. The transition at my output is completely dependent on the delay offered by the net signal, D flip-flop, propagation delay of the D flip-flop, and delay offered by the buffer signal. In this way it happens, global propagation delay. So I am just leaving it to you as an homework. Please find out for this circuit what will be the capital TSU, capital TH, where my input signal is LD relative to clock. Okay, thank you, have a nice day.